and he is forward at our Institute of Nucleus. His PhD was from Mumbai, and then he joined the Star Institute as a thinker, and he has research has made significant contribution for both low energy nuclear strategy and high energy physics, both instrumentation and theory. In both fields, he is very expert in our country, and he declares structural physics. He has carried out some pioneering research, including high-speed spectroscopy and magnetic rotation, triaxial nuclear shapes, and in case of high-energy physics, he is the leader of Alice collaboration in our country, and serving the project leader in India and collaborating with other countries. And his work in global and plasma and contribution greatly influence our next generation. Now, throughout his distinguished career, he has inspired both of us and also even the younger generations. So we are greatly welcoming Professor.
Thank you very much. So, good afternoon, everybody. So, first of all, this is something very informal. I try to tell you that something about quantum rotation. Okay, so any point of time, if you feel that I am not being transparent, stop. Ask the question. I try to answer as much as I can. The second part is that I am not using any mathematical expressions. So, mostly we will use intuitive arguments to understand that what we see experiment. So, the idea is that we do an experiment, and it is true for any field. I mean, whether you, as Shubhendu said that I'm basically accelerator physics, so I do experiments at accelerator centers in India and also at SINP. So, but then the idea is very simple, that you get experimental data. It's a data which you get is highly objective. That means whoever does it, if you have done the analysis properly, everybody will get the same result. Okay. However, the interpretation of the data is highly subjective. That means the same set of data can be interpreted in multiple ways. This is true everywhere. So, which is the exact right approach? That needs to be sort of tested again and again through various data sets, and that's how we make a progress. That means a single data set may be interpreted in terms of a specific model under specific assumptions, but unless that same model can explain a wide spectrum of data, we don't accept that model. Okay, so that is the beginning remarks. So, okay. So, although we will be talking about nuclear physics, but let me first tell you that collective rotation, that is a collective motion of a finite system. What do we mean by finite system? That means, let's say, thousands, hundreds of thousands of quantum particles. They can be bosons, can be fermions, that is a finite system. And what is their collective behavior? That is that how they behave in a collective way. It's very interesting because okay, there are, you know about Bose-Einstein condensation. There are also issues of example where I show here. You can see that nowadays this is quite straightforward to do. That is, you can have ultra cold quantum trap with lasers, and in this case it was a optical dipole trap. That means that you also use a dipole magnet for the trap. So the advantage being is that is back then you can change the field suddenly. And if you do that, this track it oscillates. And this paper was a seminal paper where they saw a phase transition between the bosonic condensate state to a fermionic state. So this was a seminal paper, and this ultra cold collection of about 10 to the power 5 lithium 6 atoms. For me, it became interesting that what you see here. These are the two condensate states, but in between there is a state where these atoms are strongly interacting with each other and they show a collectivity. That means what? That when I split the trap, it starts oscillating. See, all the gas molecules are oscillating simultaneously. So that means they are having a collective motion. Okay? So these are examples of having finite system collective motions, but which takes a lot of trouble to sort of set up. But we are lucky that in nature we have nucleus. Nucleus, as you know, is a set of strongly interacting finite fermion system. There are a certain number of neutrons and protons, let us say about 100, 200, the finite system. And in addition, these are strong, they interact with each other through strong interaction, right? So strong interaction. And that is the nucleus. Now, if you look at our periodic table, this is our conventional periodic table, which we do from the chemist point of view. Okay? The chemist point of view, and each one of them have certain number of stable isotopes. So you have about 120 nuclei, and you add average number of some isotopes, 3. So about 350 to 360 stable isotopes are known to us. However, when you allow a nuclear physicist to look at the same periodic table, he makes something which is called same-base chart. So that's a completely different. There are about 4,000 nuclei. Now the question is, where does all these nuclei come from? That means that out of these 4,000, only about 300 are stable, others are unstable. So it synthesizes them in the lab. Okay? So these are all nuclei away from the same line. All these nuclei are synthesized. Now the question is that how do we synthesize this nuclei? Okay. And why do we synthesize? So there are various interests that why we want to study a finite fermionic system. Now, as I started with the example of a collective excitation, let us look at another collective excitation which is very interesting, which is rotation. That is, if I try to rotate a finite fermionic system, then what happens? It's a quantum system, so I want to rotate. So it's a quantum rotation. Now let us look at, so unlike the similarity of the one-to-one correspondence between classical mechanics and quantum mechanics in terms of angular momentum, linear momentum, situation is very different. That means that in classical rotation, your angular velocity is an observable quantity. Now let me explain. I forgot to take out the goodies. It's too easy to explain. Okay, so this is a sphere. Okay, now I rotate it to a cylinder because the angular velocity is observable, right? Unfortunately, in quantum rotation, the generator for angular momentum, the generator for rotation is angular momentum. Okay? And what is the observable? Observable is change of orientation. Now, I rotate it. In a quantum mechanical situation, there is no change of orientation. So that means that the wave function, whether in this situation or this situation, I cannot see any change of orientation. The shape is the same. So there is no concept of any change of orientation. So rotation of a spherical object is not possible in the case of quantum rotation. It's a fast derivative. And secondly, obviously, it is a rotational energy is a continuous variable, and here the rotational energy will lead to discrete energy states. It's a quantum system. And here sorry, we should be square. So this is the expression for your energy, we know momentum is omega square, and for a quantum system, it has a dependence of I into I plus 1, where I is the element. And this is again the moment of inertia, same as the moment of inertia we talked about. Okay, so this is basically we are trying to look at quantum rotation. So this is, and you will see as we progress, and I am carrying these objects. That means we will try to draw an analogy of quantum rotation with classical objects. Okay, and try to understand that what the nucleus does. So what is the experimental evidence? Experimental evidence is very simple. You have a deformed nucleus, that means you need deformed nucleus because a spherical nucleus cannot rotate. So its energy levels becomes hypersonic because one neutron jumps to another orbital or a proton jumps to another orbital. And then the orbital energies comes into play. And they are quite random in energy. So these are some hypersonic. But when you have collective rotation, then the situation changes. It is a EI is proportional to I into I plus 1. So it's a uniform levels. That's what you see. So the fact that the nucleus exhibits quantum rotation is very clear from here. You can see two nuclei, one is molecular magnetic. This is strontium 8. Strontium stable nucleus is 88. And molecular stable nucleus starts from 92 all the way to 100. They don't stable. Now, so when I said that we keep on synthesizing nucleus, obviously we have motivation to do it. So what is the motivation? The motivation is that in accelerator, we really fabricate design learning. Okay? What we want. So that we design so that we can amplify some specific physics or interaction which we want to address. That means that we can adjust the number of protons and neutrons and we can synthesize a nucleus. So this is the one big advantage of an accelerator. The other big advantage is since we want to look at rotation, therefore I have to bring in angular momentum in the nucleus. So I have a target nucleus and I have a beam. This beam is typically a heavier beam. That means a beam of carbon nuclei or a beam of oxygen nuclei, can be nickel, can be calcium, and at an energy which is such that these two can fuse. That means they can overcome the Coulomb barrier between them. And once they fuse, obviously since this is a peripheral conditions also, it will start rotating. So there is a angular momentum is imparted by what we want by this reaction, which is fusion, evaporation, reaction. Now, what is evaporation? What happens that once you fuse, as long as the excitation energy is more than 80 MeV, particles will keep on coming. And once the energy, excitation energy falls to 80 MeV or lower, then particle emission stops. But the nucleus is still excited. So it sheds its excitation energy by emission of particles. So, and this particle doesn't take out much angular momentum. That typically 1 unit of H plus. So not many. 3-4 particles goes, so only 2-3 H plus of angular momentum is lost. Units of angular momentum is lost. But the remaining is here. So we can populate nucleus with very high excitation energy and angular momentum. So we can replicate the rotation and explore what happens to quantum rotation. So these are the accelerators. So as you are starting your career in physics, important to know that you have a very nice accelerator at Kolkata, This is the room temperature cyclotron, and there is now also the superconducting cyclotron, both working at VECC. I am sure Sukalyan will organize to take you some time to look at this accelerator at VECC. It's a beautiful accelerator. There are also other two accelerators where we do experiments. One is in TIFR, the other is in IUSC Delhi. So that is mostly for the university users, and this is for the national laboratories. So, but very clear demarcation is not there, but generally at funding level, that is how it was. And when these gamma rays are emitted, we detect them in large number of big detector arrays. You see, each one of them is a detector. I will tell you what this detector is, but these are you can see. So these are what is you have the cryoshield. So these are the detectors are cooled at liquid nitrogen temperature. So these are the holders where the liquid nitrogen is cooled. And they hold the liquid nitrogen typically for 24 hours. After that, they pour the liquid nitrogen. These you see are the transfer lines for pouring the liquid nitrogen inside the duct. And this is the array, this is at VECC, that is in our next door. Okay? That is in Bombay, this is here in Kolkata. Now, what are these detectors? Detectors are hyper pure germanium. Hyper pure is a 99.99% pure germanium crystals. Okay? And there are four of them wrapped together in a geometry which is called clover. Because when you think about the clover, it goes from one stick and then you have the sort of the fingers around the. So it is like a clover geometry. So there is a gold finger touching all the four crystals, keeping them at liquid nitrogen temperature, and then you have crystals like a clover. And these are the much bigger formative efficiency than an individual one of them detected. Obviously, because it will be at least 4 times, but it is more than 4 times because of some more details, which is not so important. But this is the detector. Now, so obviously we take data. So each detector is detecting gamma rays. But then importantly, we take data in a time correlated energy data reaction. That means that when we are connecting, each detector goes through a digital analog to digital converter. So its energy is digitized, which is detected. So what we are detecting, however, we write it in a time coordinated way. That means we want to write the data such way that it is called a smooth data, but nowadays it is timestamp data, so that we know that when one detector recorded say a AC channel of 500, the other detector recorded a AC channel of. So now if I want to see that what happened to this detector, then this is the spectrum. So you see typically let us say that something this distribution whatever one time everywhere etc. Okay, so this is one. And then this is your secondary. Okay. But then what is the advantage of taking data in a time correlated way? Now you will see that now if I see once want to say that what is the coincidence spectrum of detector 2 where detector 1 detected an energy of 5. Whatever design, let us say 500 kg. Energy equation is 500 kg. You see, then, and then you have 1,000, 100, another 100. So you in 100 you have 2 counts, 1 count. So you can generate a gated spectrum. That means that what is happening at the time when certain energy is deposited in one detector, what is happening in the other detectors we know. So that means that we land up with the zigzags. So we put gates and we see various spectrum like here. You put a gate, you get a spectrum. So now, for example, what will happen if I put a gate here? This is the energy, E1. You will see all these gamma rays to be in coincidence with that. all energies. Okay? But not so that is what I will see if I put a date. I see E2, E3, E4 on the way up. However, if I put a date on E6, what will happen? I will not see E2 because this is not in coincidence with this, right? So I will not see E2, I will see this. Okay? Okay? So depending, so when we put all the gates, we get various type of coincidence information. So it is like a zigzag with a unique solution. So then you put everything together. That is something which is a bit tricky. It takes sometimes some amount of time, but you generate at the end a excited level scheme like I have drawn there. It looks a bit more complicated, but that is how it is. So as I told you that this is the rotation matrix. This is your the moment of inertia, and this is your. So therefore, this is your. What we call as the angular part of the wave function, that is your expectation value. So I have J as I do that is I one. Now, one thing you should always remember when I show you the resonance spectrum, that is why I am showing you again this one, that a nucleus which is deformed can have, will always, it is an axially symmetric nucleus. That means that if I cut this nucleus in the middle, the cross section is a circle. It's an axially symmetric nucleus with one symmetry axis. Okay? This shape is called a polaric shape. Okay? Now, this one, most importantly, has a reflection symmetry. That means that if I do this, there is no change of shape, right? Again, no change in orientation, no change in shape, it's identical, right? So, since it is a system of fermion with a reflection symmetry, this you will learn probably this year itself that since there is a time for the anti-symmetrized function, there is a time for minus 1 to the power j, where it is the moment of inertia. Then if it is odd, then it picks up an accelerated sign. But we know it cannot pick up an accelerated sign, the wave function cannot change. Not because they are the same. Therefore, the odd speed states have to drop 1, 3, you will not see that. Only if it is an even nucleus, by the way. You see, that's what it can make. Okay? So you get various spin, you get energy, you get the parity, okay? And this is what we call as a level. Okay. So as soon as I get a level, what I can do is that I say that quantum rotation, right? Therefore, I should see EI versus I into I plus 1 phi plot, I should get a straight line. Interestingly, you do start with a straight line, straight line, straight line, and then another straight line. And you see the slope is continuously decreasing. That means the moment of inertia is continuously increasing because the slope is inverse of moment of inertia, right? So moment of inertia is continuously increasing, and in fact, it reaches a value which is very similar as you can calculate from classical shape. If I take a classical shape, if I calculate it with the deformation, let's say this is important. The value of the moment of inertia is 7. So very interestingly, a nucleus at high spin is capable of showing classical rotation also. An object, quantum object, but it truly gets frozen. All the configurations can be frozen. There is a reason for that we can discuss maybe sometime in the future. Okay, so interestingly, this is not the only shape. This shape is where is your project? This shape. Okay? There can be oblate. Oblate shape is not very difficult to imagine. You can imagine that this is not really sphere but slightly tapered on the two sides, which really it is, because while machining it becomes slightly tapered. So this is the oblate shape. Okay. This is a floret shape. And in between, you can have an object which is called triaxial. Why? Because if I take this, here also I cut it in the middle, I get a circle, right? But imagine a shape where if I cut it, I get a ellipse. That means that the three axes, all of them are different. Okay? So then, that is called a triaxial shape. Okay? So since I don't have an object like that, so this is the so you can imagine that is the axis this way, and that way. All three are same. Okay. We will come back to this shape. These are all actually symmetric shape. This is actually a symmetric shape. And other than that, you can also have very interesting shapes like this. So, what are those shapes and what is this? We will come back later. So, now what we will try to do is that we see that there is a multitude of shapes. But if you think about that talk which we are discussing today, supposed to discuss, is that what is the effect of shape on quantum equation. So now you see that how I am going to correlate, because there are various possible shapes of the nucleus, and you can now try to see that how these different shapes work. And can we understand intuitively that these rotations of different types of shapes without doing any complicated mathematics. So obviously, since we are dealing with quantum mechanics, we use symmetries. Now, what are symmetries? Symmetries basically describe the properties of space-time in particles which remains invariant under any transformation. So in this case, our transformation is rotation. So something remains invariant. Okay. Now, so what happens is that as soon as I start rotating now, imagine this thing, this is very important. I have the symmetry axis. I have three rotations, right? One is this rotation. This rotation doesn't change the orientation at all. So this rotation is not allowed. This rotation is allowed. So I go this, I can see a change of rotation. So this rotation is allowed. And this rotation is allowed. Okay? So two rotations are allowed, but since these two axes are identical, because the cross section is a circle, so therefore the moment of inertia on both the directions, so I do this rotation or I do this rotation, the earth is the same. So basically, I can do anyone. So, however, I will be talking about these kind of rotation, which remember that this is quantum mechanical rotation. What I am showing is a classical rotation. So these are discrete operations, and I am showing you three operations. One is a rotation which is this, one is a rotation which is this, and then coupled with a time reversal. Okay, so that will come back. So I will explain to you later what is time. And other is parity. The parity is very simple. You put x2 minus x, y2 minus y, z2 minus. If anything changes, this shape, think about it. Think about the origin at the middle of this object. X2 minus x, z2 minus x, y2 minus y, z2 minus x. Nothing changes. So this is invariant under parity. But now I show you another shape. This shape is more like a pier. Okay? Pier means that what we see in our NASCAR. So, see that this side is wider than this side. So now if I do it x2 minus x, and if this is z, I do z2 minus z, it becomes this. So the parity is not constant. If I do parity of operation, it changes. So bring it back, I have to do a parity, and then I have to do another reflection. Then I can bring back. These are all the symmetries we will be talking about. So these are the three symmetries. Now, so let us now start what we see and how the symmetries are related. So these are the three symmetries I just talked about. And when I talk about the time reversal, the easiest thing is first we have a whole cycle. This one. So imagine that I have an unpaired particle. So it is going like that. Okay? So its angular momentum is pointing out like that. The nucleus is rotating. Okay? And let us say a neutron is going inside the nucleus like this. So angular momentum will project out like that. So that is your rotation. This is your momentum. Now, if this is the case, I rotate it this way. Okay? 180 degree. Okay? What happens that it goes from here, goes down like that, right? Now if I got time reversal, this object was rotating like that. Now it will start rotating like that. So it will go, right? It will go back to the original. So by the rotation of 90 degree and the time reversal, I can go back exactly to the same shape where I started. So that was the shape. I went like that and then same shape as I started. So as long as we have this axial symmetry and we are rotating it in a discrete in a specific plane, I can always bring back the shape by doing this transformation, a time reversal and the rotation like that. Okay? So that quantum number remains. Now the quantum number which we associate with it, the name doesn't matter. We call it sequence. So that the details, one day if any one of you go into nuclear physics research, you will, or nuclear structure physics research, you will go into the details are not. So again, you see, this is a level scheme. Now let me see a transition like this. This is a Kumar, right? That is what we are doing. Kumar with energy, let us say 999 kV. It is a electric quadrupole transition because it takes away 2 units of angular momentum, so it is a quadrupole transition. The gravity doesn't change, so it is a electric quadrupole transition. Here, one unit will change and the gravity doesn't change. So one unit is dipole, and since in the dipole the gravity doesn't change, so it is a magnetic transition. So these are called M1 transition, these are called E2 transitions. Okay? Conventions. As per the multipolarity of the transitions. Now if you look, so for example, why I gave this gate, you can look quickly that like 491 means this gate. If I put this gate, I will not see this transition. 959, you see there is no 959. I will not see 968, there is no 968. Other than that, I will see everything. Okay? So you take any other transition, you take 531, let us suppose you see somewhere 531. Or something like, let us suppose you say 980, 980. You will see all the transitions. So that is how when we see a data spectrum, we try to make this realistic. Okay, here is not from one data spectrum, but the most important thing here, why I am showing you this realistic, because look at this gamma ray energies. There is something interesting. You will see that there is a staggering. If this is low, this is high. High compared to this. This is again low. This is again high. This is again low. This is again high. So if I plot these M1 energies, why it refuses to change? Good. So if I plot this object, that is the difference of these energies, then I will see staggering, right? This is a very typical property of signature, what is called signature split. Okay? So when you see this, take me as a holy, somebody who is preaching to you as a holy gospel, that this is what is called signature split. One day, if you are interested, you will learn that why this is called signature split. But when you see this, we tell that okay, signature is a control. The splitting is there. And you see the signature lines. However, so this is the experiment we did later. In fact, this is the experiment we did earlier. And there, if I plot the same quantity, look at 104. These two we will do, if somebody else did, these two we did. You see, there is no study. But what is the difference? Both are silver isotopes. Okay? In one case, there are 63 neutrons because it is 47, it is 63. The other case it is 61. Oh, sorry, 59. So, hardly few neutrons differ, but the behavior changes completely. Now, how do we understand this again in a very intuitive way or from some symmetry? What happens that this is well and good as long as we are considering the rotation is around the principal axis. That means there is a principal axis, we are rotating around the principal axis. Now, if I like, now I tell you, so there is this 180 degree rotational symmetry, right? Now, if I tell you that I am not rotating it around the principal axis, so what is called a tilted axis rotation, that is tilted with respect to principal, I think. Now I rotate. So after 180 degree rotation, it is not the same shape, right? So I can detect the difference. So it was this, I rotate it was like this. So this rotation, y rotation, perpendicular to the z axis, this rotation is no longer respected if I say that the rotation is not along the principal axis. Okay? So we assume that, and if we assume that, it is called, and then we study the nucleus, which was very interesting. This is again a silver isotope. Here you see, these are the M1 energies, what I said, signature splitting. So low, so high, low, high, low, high, low, beautiful. And then suddenly these are all again delta equal to one transition. 31 up to 29, up to 29, up to 29, each carrying one equal. These are all in one transition and their energies increases linearly. So initially you have staggering and then linearly it is more staggering. So something interesting happens here. So you have a principal axis rotation. That means something which was rotating like this, a nucleus which was rotating like that, something happens. What happens is, okay, there is a rotational alignment, and because of that, the rotation axis changes. So it tilts the nucleus. So you see how beautifully, that looking at these symmetries, even these very intricate quantum rotation we can visualize. And this rotation now becomes this rotation. So it is a tilted axis rotation. And the splitting completely vanishes. And interestingly, this whole process can also be very simply thought of through a geometric mode. Sukalyan did a lot of work on this during his PhD time. And they developed a very beautiful model. And it's very beautifully demonstrated that how it is like the two angular momentum vector, which they close, and as they close, angular momentum increases and the energy increases, the discontinuity again increases. So we assume that we call it like a shear, like a cast, with which we cut the trees, the shears. So the shear is closing, you can see it starts, closes, and here the energy again drops, it reopens and closes. Interestingly, doing such geometric model, we can explain the level scheme, we can get these energies and most importantly, the transition rates. Now, when we get this, we also ask that if this is true, that you can have a shear like that, one plate shear, can we have a two plate shear? That means like this closes like that. So can there be a two plate shear? That is also seen, because if this is true, as I said, that then you have to always look, if you say a effect, there has to be a generalization of it. So a single shear also says that then nothing stops nature to have a double shear. So do we see a double shear? Yes, exactly. And if we do this kind of a simple double shear model, okay, you see that's how it starts with the two blades open and then they start closing. Okay, and I can reproduce the energies of the states, and not only that, I can also reproduce the transition rates. So I have measured the lifetimes, and we measure and we get the transition rates. So everything can be reproduced by such a simplistic geometric model, all geometry which is explained by the simple symmetry that the rotation is not a principal axis. Just this assumption can be no mathematics, no determinants. Now let us think about another situation where we break the second boundary. That means that previously we broke this by saying tilted axis rotation. Now we say that okay, we now take a triaxial nucleus. That means that you remember that all the rotations which I was talking about were all happening in one dimension. That means it's either, so it is perpendicular to the symmetry axis, right? So it's a one dimensional rotation. But if I have, because around the symmetry axis, the rotation is not possible. Okay? And the other two rotations, this rotation and this rotation are identical. However, if I have a nucleus where the three axes are different, then it can rotate independently around all the three axes. That means it's a three-dimensional rotation. So we have a tilted axis rotation now in three dimensions. So it is not only doing this, but also doing this. So it is a motion like this, a three-dimensional motion. If you do that, interestingly, now you have three different axes, and you know there is a concept of bidirectional. The right-handedness and left-handedness. Right? You cannot map this one to one. They are not mirror image of each other. I think you know, right? Your left-hand is not mirror. So this is, you can think, since there are three different axes, you can think that I have some proton angular momentum around x, one axis, neutron angular momentum around one axis, and the rotational angular momentum, the fact that this is rotating, that is another hard axis. So we can have so-called a spin chirality. So again, when we say that we break this, we say that we do expect a spin chiral band. And this was a prediction just from the symmetry by a physicist called Stephen Prof. Okay? So you can see this is a left-handed system, this is a right-handed system. So if I now give it a rotation like that, okay, so Ry pi, and then I do a time reversal, I do that position. Right? So that is your transformation, and that is understand that. But you can map your left hand to right hand only by yourself. Okay, so this band was exactly seen in a nucleus called cesium-128. And since it is a spin chirality, the nucleus is identical. Only difference between one is a left-handed system, the other is a right-handed system. There is no other difference. So the transition rates are expected to be exactly the same, which was found. The moment of inertia, which is the slope, was expected to be the same, was found, and people said that first observation of spin chirality. So that was also seen from the idea of very simple spontaneous symmetry breaking in this atomic nucleus. That if you on breaking the symmetries, we see one after another. And such type of examples were found in multitudes of nuclei in what we call 30. So this was established. Now then what happened was that in mass undertaking something interesting happened. There was this paper by Amal, and they were showing a lot of bands whose moment of inertia at the two bands, like you saw in case of cesium, is very simple. So they wrote a paper saying that they followed it up with a number of papers in silver, technetium, ruthenium, and they claim that these are all chiral. So there was a test of it, which also populated a nucleus called silver 106. And there you see that this kind of doublet band. You see there is 15, 15, 16, 16, 17, 17, like that. So there is a lot of the doublet band and a very similar structure of them. So there are like M1 transition, E2 transitions at the same. So we measured the lifetime. So if you look at the moment of inertia, they look very similar as Raman found out. But when we measured the lifetimes, they were very different with our errors. So then we first said that basically the partner band originates due to the triaxial deformation, rotation of the triaxial shape. It is possible to generate such partner bands, but it need not to be a spin chiral case. For spin chirality, the transition dates also have to be identical. So then we ruled out this a multitude of these type of claims in this mass. This we can go on. There are many such examples. Now the last place I come where we do something very dramatic. That is, we break parallel. Now this is something. The reflection symmetry is something which is very holy. That generally in a quantum system, whatever quantum rotation you see, whether it is among the, as I said, the finite gas molecules, finite number of gas molecules, or collective rotation of quantum dots, they are all reflection symmetry. The nucleus, on the other hand, is the only system which sort of, in a very, very restricted mass region, shows you shapes which are like this. And as I said, this is reflection asymmetry. If I do parity operation, it changes. So, this, however, parity operation followed, so first of all imagine, so I rotate by pi rotation and then I do parity rotation. It's the same shape, right? Okay? So this is then this quantity, pi rotation and parity, these two discrete operations put together makes up generates a new quantum number which is called simplex, which, so you know, for any quantum motion, there are quantum numbers associated with it, which are constants of motion. In this case, it is this quantity which is in one word of the simplex one. And this is pictorially shown here. And here something interesting happens. Since parity, you have seen always in case of these doublet bands, you have 10, 11, 12, 13, 14, 15, like that, but they are all same type. That means that you are seeing either M1 transition or E2 transition. Parity doesn't change. But here, what will happen, the parity is no longer so good. So you will see a 4 plus, a 5 minus, a 6 plus, a 7 minus. So the parity will keep on oscillating along with as you increase the speed. So the transitions in between will no longer be M1 transition, but this will still be a dipole transition, but the parity will change. So there will be E1 transition. These are electric dipole transitions. Okay? So now let us see what we know. Now I give you a very simple exercise. You can try this, you can try it on your mobile also. So you see these shapes when we generate, okay? How do we think about these shapes? These shapes you just generate by elemental code, like P2 cos theta, right? So you have a second order term, P2 cos theta, it will give you a shape. And if I want to generate a shape like this, then along with the P2 cos theta, I also need to generate this smooth, right? This smooth has to be generated. This smooth is generated by the beta theta. So this is what we call as a quadrupole deformation, and this is called as an octupole deformation. This beta is called quadrupole deformation. Okay? So you have the second order polynomial. And this is you know the expression, right? The expression by 2. So what you do simply, when you plot this, you can do it on your mobile. You will see that you see a graph. So 1 meter. So the nucleus sits here, okay, at 0, and the beta 3 is 0 in this case. However, now I put a p theta. Okay? So if you are using the expression, put beta 2 like 0.2 and put beta 3 like 0.1. Okay? And you plot. You will see this very interesting shape with these 2 minimals. Okay? So you have exactly symmetry around the 0. If 0, you will get 2 minimals. And these 2 minimals corresponds to these 2 simplex quantum numbers. I said that simplex quantum number. So when the shape, so the nucleus either it can sit here or it can sit here. There is no difference. There is no difference otherwise, no change in shape. But just because it is reflection asymmetric and there is a beta 3 term, there is an option you can either sit here or sit here. If this is a simplex, let us say this is simplex quantum number 0, then this is simplex quantum number 1. And what will happen is, as you expect, you see, again, it looks like 2 bands, as you saw, transitions between the 2, like the signature bands, but these are now, instead of signature doublets, these are parity doublets. So, one side is positive parity, the other side is negative. So, complete in 5 minutes. So what we did, sometimes he is a bit unhappy to my. Okay. So what happened was that no, I think there should have been another slide. This is an interesting slide because I just thought that in one case I will tell you. So this is what was done at VVCC. So this is the kind of experiment. You take alpha mu, you put it on a molecule of 100 target, which is a rich target, and after that, with 4 neutrons, remember the compound nucleus, where particles evaporates because excitation is more than 8 MeV, 4 neutrons goes out, and you end up with 100 plutonium. Now you can ask me that how you ensure 4 neutrons, it could have been 6 neutrons, 4 have been 2 neutrons, and that is the synthesization process. That means that I adjust the beam energy in such a way that the excitation energy above the polar barrier I adjust. I put the excitation energy in such a way that there are 4 neutrons which will predominantly emit compared to 5 neutrons or 3. So I will produce this nucleus predominantly. However, a 5 neutron nucleus will also form. That means 99 molybdenum, 99 ruthenium also gets formed, 101 ruthenium also gets formed. In fact, we have also started from the same experiment. With the 3 neutrons, you have present 101 neutrons. Also, that is a completely different physics. And we used 11 Nova detectors and this digitizer, and most importantly, we took a 10-day period. Now, this is sometimes challenging. Now, when we talk about beam time means it's 24/7. There is no break. You don't go in the night to sleep because you cannot stop the accelerator and go home. A typical accelerator costs about 60,000 rupees to run per day. So you don't switch it off. So you sit, you collect data. And 10 days is not trivial job. So generally what do? You motivate the students. You say, something great is going to happen. If you take this data, something great is going to happen. So that is important. You see that when you are working in a group, and if you have to first have a strong physics motivation, and you have to be able to transmit your excitement to others, because everybody will put in a lot of effort to collect this data. 10 days is not easy. Because at every shift there are 2 persons. It is an 8-hour shift. So imagine it is not an easy thing. So we all sat together, we took the data, we believed in ourselves that something interesting will happen. And then, which was never expected, that in this lighter nucleus, in this case mass 100 region, you will see this kind of T1 condition. This was not seen before. So whatever you see in red, these were not seen. Now you can ask me that why it was not seen. And why did we sat for 10 days? Now you see what happens. How tricky it is. So we are talking about this. See, this is a gate. Okay? This is the kind of intensity you see here. You almost see nothing. Okay? These are what you get after sitting for 10 days. So these are very, very weak transitions. Now you can say that, yes, you can do an estimate that if we get E1 transitions, then how long should we take the build time? Accelerator people, that yes, we will not do that because there is no point. Because I will not see this transition. Anyway, after 10 days, this is what I see. So there is no point to do that like this. So if you can convince your friends, the accelerator friends, they will give you 10 days build time. And then that's something which was quite unexpected to the international community. And now you also measure the transition rates, okay? So by you see these E2 transitions, which are among the bands, so these are E2 transitions, right? Same parity, how we measure. Again, sometime maybe. You see, interestingly, the E2, I grew up with a microscopic model, very complicated model. I also don't understand very well. It can be done. And then the transition rates are more or less reproducible. But when you go to the electric dipole transitions, which are really the signature of octopole deformation, because without octopole deformation, this parity mixed, the parity changing transition will not be present. Those transition rates are way above, it's a lower mistake, way above than what is expected from the theory. In theory, this is a theory which does not include octopole deformation. Now you say that why there is not a line? But what happens with octopole deformation? The answer is that currently we still don't have any theory at even national or international level to do this calculation. Okay? So there is a group with whom we are collaborating in Kashmir University with my very long-term collaborator, Javed Sheikh. When I was doing PhD in PRFR, he was a postdoc. So he has a very interesting book, which is called DPSM, which he wrote completely by himself. And he is now incorporating this beta 3 term in the code, that is incorporating the octuple shape and then do this calculation. The problem is that why this model doesn't explain. Now you see, this is what we have to do. But what we believe that from the transition dates, how Sukalyan 100 compared to, let us say, a well-known octuple deformed nucleus, which is sodium 226. It's simply not a good mathematics. So you see that this object, the octuple beta 3 deformation, is much bigger than this. So this you can see by the extent of the neck. The neck is smaller here. But this nucleus rotates much faster than this nucleus. In mass rotation, is number one. And number two, the most biggest problem is that this octuple deformation is built on a shape where there are two unpaired neutrons. This is the problem with the theory. The theory which we have currently in the market, in the international market, which is with no quasar. So they can do a calculation for this, but there is no unpaired nucleus. But the octuple deformation which we saw is built on a configuration where there are two neutrons which are unpaired. So this becomes a problem. So this is an open problem to the theoretician. We have a data already which is there in the market. I also know a group who are in the US who are trying to reproduce this one. Now, you can then ask that, so what happens if we break all? So, do we know anything about it? See, if we break all, that means a nucleus which is reflection asymmetric and there is no axial symmetry. It is like our heart, the shape of our heart. So that means you think about the heart. So don't only think that it is typical line. So not those red balloons. I mean, you have to think the red balloon, but without the tip. So these objects, heart-shaped nucleus, these are not really experimental yet. So this is a challenge that if somebody can find out a possible candidate and try to look for this nucleus. We have been trying. We have tried two nucleus. One we were pretty close, but somehow at the end we got. But we are at it. We have some more plans to work it out because this nucleus has never been seen before. A heart-shaped nucleus, a rotating heart-shaped nucleus has never been seen. Okay. So, as you see that whatever we discuss, these are all the work of my research. As I said, I did nothing. Okay? I gave a word, basically try to motivate them to work hard. They will work hard. And then they do beautiful analysis, do all the difficult work. Okay? And Manindita, who is my last student, she has a very interesting publication on nuclear opening last year. This we have not discussed because of the paucity of time. I'm already 5 minutes more. Okay, so as we just saw, that the nucleus can be a lot of surprises. And that's what is an experimentalist. You are expecting that you know, you understand. So as an experimentalist, that's what is to be your mode. That you hope that this is going to happen. If this happens, then there is nothing interesting. You put a finger on the water, the water boils. There is nothing experimentally happening interesting. But when you join your research, and if you become experimentalist or a theoretician, when you are doing research, all you are expecting that accident. And then you have something interesting. And then you have a new science. So today we looked at symmetries. Remember that what we see all around us, we do see evolution of symmetries, right? So what are not looking at the 60-degree symmetry, and 180-degree symmetry, rotational symmetry goes to the 60-degree symmetry in case of snowflakes. So this also happens all around, always. So nature is all beautiful all around us in all its complexities, be it in macroscopic scenario or be it in quantum rotation. Thank you very much. Okay, now questions. Any question which comes to your mind, you tell us. Nothing. Doesn't matter. Okay? So if you have, but you could have asked any question, it doesn't matter. Yes?
In the case of double potential that we have seen.
Huh?
Here.
Potential.
Double potential.
Double potential. Yes.
So two radiated polynomial. Yes.
Yes.
This one. So this second one,
Hello.
it is symmetry.
Yes.
It is symmetry.
This is, yeah. So, yes. So this is symmetric with respect to this beta equal to 0.
But I do not understand why this cubic and linear term here.
Why I need a beta theta?
Yes.
Which one?
Cubic term and the linear term that will break.
No, there is no. Oh no, this is P3 cos P3x. I am not doing any extra thing. I am just saying that you will plot because see, when I want to generate a shape like this, okay, I need a P2 cos theta, right? A second order Legendre polynomial along with a P0 term, right? And I generate this. Now, if I want to generate this shape, that is, there is a, so I need a quadruple term, that is a second order term, and I have to also mix up other. So this is P3 cos, and this is P2 cos. And okay, there is amplitude, which is measure of the deformation. So as I said, that you can put beta 2 as 0.2 and you can put beta 3, which is a higher order deformation, half of it, like 0.1. And that is exactly what is called.
If y symmetry with respect to x.
So this is exactly what you see. That is the symmetry with respect to which is the beta. This is beta 3, this way is beta 3. That means that in this case, this is x. Okay. So it is symmetry with respect to the 0. Okay. So I am plotting y as this. Okay. And in this case, it is exactly so. I am writing this as beta 3, that this is 1 minus beta 3, this is plus beta 3. Otherwise, what I am plotting as, I shouldn't have be writing as b and it have written as y. So y equal to this, because it's a potential, I wrote b. So you see that you get two minimums. In case of when you put only 2 cos theta, there is only one minimum. Okay? And what I am trying to tell you is that the fact that this reflection asymmetry, that is the breaking of the parity quantum number leads to this kind of two minima, and each corresponding to the rotation and the quantum number which I defined as a simplex quantum number as this as a one quantum number.
If you change x to minus x,
If I change to x to minus x.
so y will not be symmetric.
No.
If there is a cubic term.
It is yes. What happens is that you have a cubic term. See, there is a cubic term. P3 cos theta. See, that is the main difference. Let's see. This is x to minus x minus square. But here there is a problem. It's a cube. That's what makes me difference. That's exactly the reason. So that is exactly is the reason of the breaking of the reflection symmetry. Such that you have one corresponding to what x, the other is y. So they will look very similar because all the amplitude terms are the same. Only I am making x to minus x. So this will become minus 5x cube plus 3. There is no other. So I can take a minus sign out. So this is if this is this one, then this is in the minus. So but then that is what happens. That if I change from x to minus, so you will get 2 because of this stuff. The beta 3 positive. And this is exactly the optical term. So the beta 3 terms gives you this shape, this optical shape. So this is okay.
This function does not have definite. This function does not have definite parity.
It doesn't have a definite parity. Yes.
In the second one.
Yes. So it doesn't have a definite parity in the sense that, as I said, that these two minima corresponds to a new quantum number which is called symmetries. The parity is no longer a good quantum. It is the pi rotation. So you have this shape. So I first make a pi rotation, it goes here, and then I do a parity operation, it comes to the original shape. So pi rotation multiplied by parity, these two discrete operations together is a quantum. Parity individually is not a quantum. Parity individually is not. So one corresponds to one shape or one rotation. This is not shape, sorry. The shape is the same. One rotation corresponds to this, the other rotation corresponds to this. But that means that the two simplex. The constant of motion is pi rotation multiplied by parity. That is a constant of motion. So with that we can quantify in this case also. Now you can say that what is this one? This one is one of them. We don't see that. There is in principle, there is a one set of bands here because this itself is a reflection asymmetric shape. It will generate a band structure like this, and this one should generate another one. But generally, we don't see independent nucleus the second one because it is believed that it is having excitation energy, so we can populate it. But in what nucleus is we see? We see all four bands. So that is possible. But we see generally the excitation. Yes.
Center, nucleus center to surface, the radius R is written as somewhat while.
Yes, the shape.
How we can write in terms of radius and radius?
So if we go to the how we define the shape of a nucleus, okay, here. So that is your radius, okay. So you have the y LMs or lambda mu's, okay. So this is the origin of your Legendre potential, right? So with lambda equal to 2, we generate the octopole shape, which is this. Okay? Sorry, this one. With the lambda equal to 2. And if we put lambda equal to 3, that means P3 cos theta. Okay? Then we generate the octopole shape, this one. So basically, we are changing the radius term. That's all. We are changing the radius. And it is the part, since it is part of your mean field, okay? Because V of R, so you will put it as a mean field. So that is why it is the mean field which you put in breaks the various type of symmetries. So since we said today that we will talk intuitively and not bring in too much of mathematics, so that I avoided that part. But that could have been easily approached. That you can take a mathematical approach and demonstrate that how different lambdas, and what happens that if I put not only y30, but I put y31, because I have LM, right? YLM. So I can put L 30, 31, 32. So all the shapes are different. Okay. And as I said, you can plot all these shapes very trivially in mathematics to convince yourself how the shapes look. Just put it in mathematics as you plot it in mathematics, beautiful three-dimensional shapes. These are all called spheroids. Right? Okay.
What is the prime signature to being a nucleus chiral?
Huh?
What is the prime signature to being a nucleus chiral? You have said that energy, level energies and B2 values must be same.
What is the signature of chirality? So, as a level scheme wise, the chirality basically is like this. That is, what you expect is 2 4 plus k. Again, these will be all same chirality. There is no quite figure. So you will see 2 5 4 plus k, which are mostly degenerate. 2 5 plus k degenerate. 2 6 plus k degenerate. Because you see, what happens? You think logically that this is basically like you are having a shear span, like the same thing. Like you have all spin states, right? It is not a principal axis rotation, it's a three-dimensional, so it is tilted. So you will so since it is tilted and the rotational symmetry is missing, therefore the odd spin states need not to be vanishing. So even state, odd state, all will be present. Okay. In this case, it is the same. So you have all 4, 5, 6, 7, 8, all. First of all. Secondly, you have two sets of bands. They are nearly degenerate. That means this individually looks like a signature band or like a signature band. This for 1, 4, 1, 5, 1, 6, 1, 7, 1. It makes a signature kind of a band. The other one makes another signature band. So there are two signature bands whose, like here, you see, okay, I should have shown HAPIFA level scheme, which is a very conventional level scheme. But you see, like this example, I have a 14 minus, I have a 14 minus. Okay? I have a 15 minus, I have 15 minus, a 16 minus, 16 minus, 17 minus, 18 minus, like that. So you have bounded structure. Okay? So you have one signature band. Okay, there is two signature partner, one signature band, another signature band, but they are energetically degenerate. That is energetically the signature of spin chirality, but that is not the only signature. The transition rates also needs to be identical because there is no difference in the two nucleus. In one case, the spin coupling is left-handed, the other case it is right. So all the transition rates have to be identical. And only one nucleus till now, cesium 128, has passed this criteria. Only one. No other nucleus had. There are debates. You go to international.
Is there any analytic prediction of that?
Huh?
Is there any analytic prediction of that? The level energies and B2 values must be identical.
Which one?
I need to know that. Is there any analytic?
Yes.
Yes. Yes. Yes.
We can name and
No questions for youngsters. So I confused you thoroughly, right? Completely confused. Okay, good. Nothing wrong. So, but it's important to realize that something interesting can be done in our country. Okay. So that's very good.
thank you.
Okay. Thank you.